All right. This video is going to have a bunch of different topics in it that are just things that it's important to clear up right now. The first of which is a little bit of a kind of a helpful tool in cases where you have an object that has gravitational potential energy and it's moving to a location where there's not as much gravitational potential energy or more. Okay, so we're going to take a look at that first. And it's kind of it's a neat little trick. It's not something that might be obvious to you without me doing this. So therefore, that's why we're going to talk about it. The example for illustrating this goes as follows. Let's say that there's a 7-kilogram cat sitting on a tree branch that's 4 meters off the ground. We want to know the cat's gravitational potential energy at a few different spots. I'm going to draw my picture first. Here's the ground. Here's the tree. Okay, it says the cat is sitting on a tree branch that's 4 meters off the ground. Here's my tree branch, 4 meters off the ground. There's my cat. We want to know the cat's gravitational potential energy with respect to the ground, with respect to a lower branch that's only 2.5 meters off the ground, and with respect to the branch that's currently on. And that language might not be familiar to you. Before we get to that, I'm just going to fill in a couple other things. If this cat is 4 meters off the ground on that branch, and there's another branch that's 2.5 meters off the ground, if this is 2.5 meters, then if the cat's 4 meters off the ground, then this obviously means that this must be 1.5 meters off the ground. Okay? So, whenever you see the phrase with respect to the ground, what that means is if the ground is where h equals 0 meters. And we talked about that when we talked about gravitational potential energy, the equation for which is mgh. You need to set a spot where h is equal to 0. So if you see the phrase with respect to the ground, that means treat the ground as where h equals 0. That means down here. Let's see here. So if the ground is h equals 0, I can figure out what the cat's gravitational potential energy is as he's up in this tree branch by using the following formula. The initial gravitational potential energy is equal to the product of the mass, acceleration due to gravity, and the initial height. The mass of the cat is 7 kilograms. The initial height, the acceleration due to gravity is 10 meters per second squared. And the initial height of the cat with respect to the ground, if the ground is 0, the cat's 4 meters above it, well, it's 4 meters. 7 times 10 times 4. The initial gravitational potential energy of the cat is 280 joules. I'm going to skip all the way down to A, and you'll see why in a second. As the cat safely jumps to the ground, what is the change in the cat's gravitational potential energy with respect to the ground? Basically, I want to find delta UG. If I'm looking for delta UG, that is always going to be the final gravitational potential energy minus the initial gravitational potential energy. So the final gravitational potential energy is going to be mgh, no not because this is the final, minus, we just found the initial, 280 joules. Well, if the cat ends up on the ground, and that's where we're saying h equals 0, this whole term is 0, therefore, UG is negative 280 joules. Delta UG, excuse me. So the final gravitational potential energy was 0 joules, therefore the difference, the change in gravitational potential energy was negative 280 joules. Let's go on and let's do the B's. With respect, let's figure out the cat's initial gravitational potential energy, when it's up here, with respect to a lower branch that is 2.5 meters off the ground. Again, what this means is, when it says with respect to, it means set h equals 0 there. So this is if the lower branch is where h equals 0 meters. Meaning, this right here is where h equals 0. UG naught equals mgh naught. M and g are the same as they were in the last example. H, this time, is not 4 meters. That's the distance the cat is above the ground. But we're saying that the lower branch is where h equals 0. There's 1.5 meters between the two branches. That means the height of the cat right now, with respect to that lower branch, is 1.5 meters above it. So h is 1.5. 7 times 10 times 1.5. Look at that. The initial gravitational potential energy has changed. It's the same exact situation, but by changing where h equals 0, we're actually getting a different gravitational potential energy. Now, the only thing that changed was our own designation of where h was 0. Why did that change the number? We're going to see right now that that number is not really important. Because if we try and find the change in the cat's gravitational potential energy, then we're going to get something that looks like this. Delta UG equals UG minus UG naught, mgh minus, in this case, 105 joules. And in this case, we're going to have 7 kilograms. We can't just say h is 0 because when the cat ends up on the ground, he's not at h equals 0. Matter of fact, if you could think about it, if this is 1.5 and this is 0, this has got to be negative 2.5 down here. So m and g are the same. The cat's height is now negative 2.5 meters with respect to that branch. He's 2.5 meters below that branch, minus 105. If I do this, 7 times 10 times negative 2.5, I get negative 175. And look at that. If I subtract 105 from that, I still end up with a change in gravitational potential energy of negative 280 joules. That's interesting. That's the same as the change that I got when I had h equals 0 at the ground. Okay? So even though the initial gravitational potential energy changed and the final gravitational potential energy changed, the difference between the two of them stayed the same. Let's see if that pattern holds. What if we find the cat's gravitational potential energy with respect to the branch that it's currently on? In other words, if this branch, the highest branch, is where h equals 0 meters. That would be pretty easy. UG naught equals mgh naught. And if this branch, where the initial height of the cat is where h equals 0, guess how much gravitational potential energy the cat has to begin with? 0. Nice and easy. Then, if we go and try and find the change in gravitational potential energy for the cat, UG minus UG naught. UG naught was 0. mgh, 7 kilograms, 10 meters per second squared. And the height, if this is 0, and we've been assuming up is positive the whole time, then the ground must be at negative 4 meters. 7 times 10 times negative 4 is negative 280 joules, and that again is what the change in gravitational potential energy is. So we see that no matter where we set the h equals 0 line, we always get the same result as far as the change in gravitational potential energy. And that makes sense because the equation that you're given for when we define gravitational potential energy, you're not just told what UG is, you're told about the change in UG. They use the variable y, I'm just going to stick with h for height. So the key here, the important takeaway, is that finding just a gravitational potential energy a lot of times isn't all that useful. What we really want to know about is the change in gravitational potential energy. That's going to be much, much more important. The reason that's important is because as this cat moves from his initial position to the ground, they're losing gravitational potential energy. They're losing 280 joules. Where does that energy go? It becomes kinetic energy. So the important thing is it doesn't really matter where you set h equals 0. You can pick whichever one that you want. My preference is make it something so that you can cross it, so that something cancels out and it's easier to calculate. So for instance, put h equals 0 somewhere that either the initial or final gravitational potential energy is going to be 0. So situation A or situation C, or those would probably be my choices. I'm spelling convenient wrong. Convenient. But anywhere will work. All right. So we're going to have ET equals ET. Initially, the cat has no kinetic energy. It's just got gravitational potential energy. Yeah, let's pick. Let's see. What do we want to do here? Let's pick A. Okay, let's pick situation A, so that the ground is where where h is equal to 0. So UG naught equals K, and then at the ground it's not going to have any gravitational potential energy. So really you can think of it as, I could have even written something like this, where, hey, maybe there's gravitational potential energy at the ground, but it cancels out. Again, remember, we always follow this format, write down ET equals ET, since we know energy is conserved. There's no forces doing any work, any outside forces doing work to take energy away. So gravitational potential energy is present at the beginning. At the end, all the energy is kinetic. Therefore, we can solve. We can figure out the speed of the cats. We know the initial gravitational potential energy is 280 joules, because h naught is equal to 0 at the ground. That's the decision that we made. And the kinetic energy equation is 1/2 mv squared. All we have to do is plug in for 280, 1/2, we got to plug in the mass. Mass of the cat is 7 kilograms times v squared. So we end up with, I'm going to do this math right here, 280 divided by 1/2, divided by 7, take the square root. We get the speed of the cats as 8.94 meters per second. And you could double check that with kinematics if you wanted to. You would get the exact same answer. So we kind of already wrote down our conclusion here, but I will just reiterate. Depending on where h equals 0 meters is set, UG and UG naught will change, but delta UG won't. It is always the same for a given situation, regardless of how you set your 0 line. Okay, so you want to set it somewhere convenient. In other words, so that something cancels out because you set the 0 line at an important spot, or somewhere, not something. And as you practice more and more, that choice will become more and more apparent. Okay, so that's just a little trick about gravitational potential energy that I think is important for solving some of these problems. It makes your problem solving a lot easier in certain cases. We're going to go now to, not so much a trick, but situations that you should be familiar with, and that is how to apply conservation of energy to systems in which you have pendulums and or springs. A pendulum, obviously, is something that, it's a very simple setup. You have, at its simplest, you have a mass called a bob that is attached to a string, and the string has an anchor point. You pick the pendulum up, essentially giving it gravitational potential energy. You release it, it exchanges that gravitational potential energy for kinetic energy because it swings down here with some speed, and then swings up to the other side. It gives that kinetic energy back, it becomes gravitational potential energy. So we've got a conservation of energy going. The energy is transferring, kind of sloshing back and forth between gravitational potential energy and kinetic energy as the pendulum moves. The above drawing shows a simple pendulum bob of mass m, that's this right here, on the end of a string of length L that has been pulled back to initial angle theta naught from its equilibrium point, which is down here, and released. The pendulum experiences negligible amounts of friction. That's important because that's your clue that ET equals ET. In other words, energy is conserved. In terms of the given variables and any fundamental constants necessary, we're going to determine 3 things. But first, let's list our given variables. We're given m, we're given L, and we're given theta naught. We want to determine the initial potential energy if UG equals 0 at the lowest point of the swing, the maximum speed at the bob, which will happen when there's the least amount of gravitational potential energy down here, and the tension in the string here and here. The first one looks like it's going to be really easy. The initial potential energy at the lowest, the initial potential energy, that means the potential energy when the bob is released up here, if the UG is 0 at the lowest point. What that's saying is that at this lowest point, when the pendulum is all the way down here, this is our h equals 0 line. So we want to know the initial potential energy when the bob is up here. And so I'm just drawing my dotted line in reference to the top of the bob. Well, in order to know that, we know we're talking about gravitational potential energy, and we know gravitational potential energy is mgh. If we're going to try and find the initial gravitational potential energy, we know the mass is m. G is a fundamental physical constant, so we can keep that. We need to know what this initial height is. We need to know how high above the lowest point this object is. So we're calling that h naught, or we could just call it h. It doesn't really matter which. But h is not one of the variables that we're given. So we need to figure out or determine h naught in terms of the given variables. And that's a little tricky. That involves a little bit of some math that you've learned in previous years. Nothing super hard, but we are going to have to do a little bit of geometry and a little bit of trigonometry. To start, let's recognize that this is what we're looking for, this distance right here. But also look what that did for us. We turned this, so by drawing in these dotted lines to show the height, we turned this into a right triangle actually, which is kind of interesting because right triangles usually end up giving us some good answers. Some other things that we haven't filled in yet. We do have an angle listed here, the initial angle that the pendulum string makes with the vertical when it's pulled back. We know that this dotted line here is length L because that's the length of the pendulum. Therefore, this is also length L. And this entire thing is also length L. And that makes sense because as the pendulum goes down, all of these are the same length, but since this is pulled up a little bit, L just it's kind of at a diagonal. It doesn't go all the way down here. That would be like saying the string is stretched out when it's all the way over here, and that's not the case. So interestingly, if this whole thing is L, the length of the string, and this is h naught, this distance, this difference in height between lowest point and highest point, then what does that make this side of this triangle right here? If this whole thing is L, and this is h naught, this is L minus that little h naught. And that's literally what the length of that side is. It's the entire length L minus the little bit that it's giving up right here. And that's interesting because now we have two sides of the triangle that we know, this right triangle right here. We have these two sides that we know, and we know this angle. This side is directly next to the angle. We say it's adjacent to the angle, and this is the hypotenuse. Therefore, we can use cosine to talk about the ratio between those sides. I can write down cosine of theta naught equals the adjacent side, which is L minus h naught, over the hypotenuse, L. I can rearrange this to solve for h naught. I'm going to multiply both sides by L, giving me L cosine theta naught equals L minus h naught. I'm going to bring h naught to the other side. I'm going to add it to the other side, subtract this term to the other side. I'm left with h naught equals L minus L cosine theta naught. And I can even take the L out of both these terms and turn this into the initial height that this pendulum bob has been picked up to in terms of given variables, theta naught and L, is going to be L times, in parentheses, 1 minus cosine theta naught. That's going to be important because I can plug this in down here, and we can see that UG naught is therefore equal to MGL times 1 minus cosine of theta. It's going to be an important result later on. I do just want to talk about this for a second because this looks a little weird to most people. It's a little strange that we're describing it like that. Okay, hopefully that's a little bit better. Basically what this says is as you draw the pendulum back farther, this angle is going to change. And think about how cosine works. Cosine is really big when theta is 0, and it's 0 when theta is 90. So if you draw this back 90 degrees, okay, cosine of 90 is going to be 0, and therefore the initial height is L. That would be like drawing the pendulum back to here, and that makes sense. The pendulum at that point, the bob, is L above its lowest point. So this expression seems to work, and it continues to work even if you don't pull it up as far, or even if you pull it up even more. Okay, that expression will continue to work to describe the initial height of the pendulum bob. Let's move on to part 2. What is the maximum speed of the bob? Well, we talked about in the beginning how speed, or how the energy in a pendulum system is constantly being transferred back and forth between gravitational potential energy and kinetic energy. We know the initial gravitational potential energy when it's released. So if we use our ET equals ET equation, and we set this as the release point, and this is the lowest point, those are the two spots that we're evaluating, then at release, it's only got gravitational potential energy. At the lowest point, where H equals 0, and because the gravitational potential energy is 0 at the bottom, it's only got kinetic energy. So the initial gravitational potential energy we just found, mgl 1 minus cosine theta naught, equals kinetic energy equation, 1/2 mv squared. I have an m on both sides. Cancel that. Multiply both sides by 2 to get rid of the 1/2 and take the square root. I'm left with a speed at the bottom of radical 2gl 1 minus cosine theta naught. That's the speed of the pendulum at the bottom, or the bob at the bottom. And again, we can say that this kind of makes sense. The more you drag this up, the bigger the gravitational potential energy will get, and you can check that as you go up through from 0 degrees to 180 degrees, you'll get bigger gravitational potential energy, and that's also going to make the final speed at the bottom bigger, which makes sense. If you pull the pendulum back farther, it's going to go faster. 1 and 2 can be solved just using energy. 3, parts A and B, the tension in the string at the 2 points, you need forces in order to do this. So now we need to draw a free body diagram. Here's our bob. And before I draw in the forces, we do have to realize that a pendulum is actually an interesting case of circular motion. Because if you were to take this pendulum and just allow it to move freely, even if you draw it all the way back up to the top and you let it move, the path that the pendulum bob traces out is actually circular. And the fact that it's circular is important because even down at the bottom, even if the pendulum isn't moving in a full circle, it is moving in circular motion. It's tracing out the path of part of a circle. So since this is going to be in circular motion, we want to align our axis so that at least one direction points towards the center of the circle. When we're at the release point, that means that the axis should look like this. Let's call this the x direction. We'll call this the c direction. Remember, c standing for center of the circle. X, and here's our plus. Okay? Our forces that are acting on our pendulum look like this. The tension points in the positive c direction towards the center of the circle. The force of gravity, as always, points straight down, and in this case, that means it has to be broken into components. One in the negative c direction, because it points directly out of the circle, and one that is perpendicular to that, kind of pointing up tangent to the path of the pendulum. These are both going to be FG, and I've kind of gotten ahead of myself. One's going to be cosine theta, one's going to be sine theta, or cosine theta naught and sine theta naught. By looking at this picture, you can tell that up here, the angle theta naught is between the string when it hangs straight down and the string when it's at this angle, when it's been pulled back. On here, we have a line pointing straight down, representing the force of gravity, and the line that is opposite, the tension, which is tension is parallel to the string when it's pulled back. This angle here is the same as this angle here. Therefore, this over here is Fg cosine theta naught, and this is Fg sine theta naught. Now we can get to our net force equations. If we're looking for the tension in the string, that means we're going to have to deal with the c direction, because that's the direction tension is in. So I would write down Fc equals T minus Fg cosine theta naught, and we remember that tension, the centripetal force is equal to MAC. Now, if this is the release point, we know that AC is really this tension. So, okay, mg cosine theta naught. AC can be substituted for v squared over r. At the release point, the pendulum bob hasn't started moving yet. So v is 0. This whole term is 0, and that leaves tension minus mg cosine theta naught is equal to 0. I can rewrite that as the tension at this point is equal to mg cosine theta naught. The tension is going to be dependent on the mass, the acceleration due to gravity, and the angle that the object is brought back to. For 3b, the tension at the lowest point, this is going to be a little bit more involved. The free body diagram arguably is simpler because we don't have to tilt the axis now because since this is the bob here. The direction towards the center of the circle is just straight up now. That's the C direction. We have tension pointing up. Notice there's no new forces, just the direction of the tension changed. And the force of gravity down. Let's move this up a little bit so we can see. Fc, the centripetal force, is therefore equal to T minus Fg equals MAC. We'll make some substitutions here. T minus mg equals mv squared over r. Now, we can make substitutions for v and r because those are not variables that we know. Notice that every other expression that we've gotten so far are variables that we were either given or constants. V is the speed, and we want v squared. So I'm just going to add this mg over to the other side right now. I'm going to have t equals mg plus m times v is radical 2gl 1 minus cosine theta naught. And that whole thing is getting squared. R, the radius of the circle that the bob is tracing out, is just the length of the string. Okay? This bob, if you let it go all the way around, will trace out a circle with a radius of length L. So if I square this thing in square root, watch what I get. I get mg plus m times, the square root just goes away, 2gl in parentheses 1 minus cosine theta naught all over L. Which means that this L and this L are going to cancel out. I've got no more fraction. That's actually really nice that it works out that way. So I'm left with mg plus 2mg times, well, it's going to be 2mg times, in parentheses, 1 minus cosine theta. So I could actually write this like this. I can distribute the 2mg to both terms in here. Now what I'm going to do is I'm just going to add mg and 2mg to get 3mg minus 2mg cosine theta. I'm going to bring the mg to the outside. What I'm left with, and you don't have to do this, but it's a nicer math step. It kind of cleans everything up. I pull an mg out of all terms. I'm left with this, mg times, in parentheses, 3 minus 2 cosine theta naught. And therefore, that is the tension at the lowest point in the swing. Now, I would take a look at these because these are problems that come up a lot when we deal with conservation of energy and pendulums. We also have to talk about conservation of energy with springs. We're going to do a very easy example. This is super quick. It can get more tricky when we deal with vertical springs or springs on ramps or other forces that are acting on our object, but the basics are very straightforward. We have a very poorly drawn spring of spring constant K that has one end attached to a wall, other attached to a block of mass M. No friction between the block and the floor. So what this is telling us, again, is that ET equals ET. The block is pulled a distance x from its initial position and then released. In terms of the given variables and any fundamental constants necessary, determine this. So let's pull the block backwards. Or let's say that I guess it doesn't really matter which way we look at it, but let's say that the block right now is pulled back to this distance, or it starts here, but it gets pulled back this far. So this is our distance x. Okay, this picture is very much not to scale. In terms of the given variables and any fundamental constants necessary, determine the initial potential energy of the block at x and the speed of the block as it passes its equilibrium point. This is another good conservation of energy question because all we're doing once the block is released, when the block is pulled back, it's got some elastic potential energy stored in it, and as it gets released, it doesn't go up, okay, so it doesn't gain gravitational potential energy. There's no friction, so no internal energy is generated, but as it is released and goes back towards its normal length, it loses that elastic potential energy and gains kinetic energy. So, at first, the initial potential energy of the block at x, let's just note that energy is added, and that energy is in the form of US naught, elastic potential energy, initial, by you pulling it back. So you did some work on it, but we're not really even concerned with that. You did some work on it, and you gave it this energy. 1/2 kx squared is the equation for elastic potential energy. Then, when you release it and the block goes back through its equilibrium point, that means when the spring is not stretched out at all the elastic potential energy is turned into kinetic energy. Again, this is a situation where energy is conserved once you release it. So this is release, and this is at equilibrium. At the release point, there's only elastic potential energy. At equilibrium, there's only kinetic energy. We can solve for the speed. We can cancel out those 1/2, and we can solve for the speed by dividing both sides by m and taking the square root. V ends up being equal to x times the square root of k over m. You might need to write out some of that algebra yourself, but it's pretty straightforward. So we can also predict the speed at this point right in the middle. This is just another situation where it's important to understand how conservation of energy works. And it's a very common situation, okay? Remember that conservation of energy is simply when it's, excuse me, conservation of energy just implies that the total energy of a system stays the same. It might change from one type to the next, but the total is still the same. In this case, it went from elastic potential energy to kinetic energy. If the spring then becomes compressed, it's going to lose kinetic energy and start storing elastic potential energy again. As long as no energy is lost to friction, this object will oscillate and be changing the types of energy it has for forever, but the total will always be the same. I believe our next unit is on momentum. I will talk to you later for those videos.